This is Unit 7, Lesson 9, and today we're going to talk about medians of a triangle. So a triangle has three sides, and each of those sides has a midpoint, which I'm going to put a purple dot on. A median is a line drawn from the vertex of a triangle to the midpoint of the opposite side. So if I go to the vertex at the top, and you can do this too if you get a straight edge, and then I connect that to the midpoint, that line is called a median. So they're three medians because I'm going to connect each vertex to the midpoint of that opposite side. That's a median. And then I have one more right here. That's a median. Okay, so we're going to do that for all the triangles. It doesn't matter if it's an isosceles triangle, a scalene triangle, a right triangle. All I'm going to do is I'm going to connect the vertex to the midpoint of the opposite side. Okay, so I'm going to take each vertex, connect it to the opposite side, that midpoint, vertex, connect it to the opposite side. And then the last one here are my midpoints. And we created medians when we did constructions. These midpoints are already drawn for us though, so we're just going to do it with a ruler right here. I'm going to take that vertex, connect it to the opposite side, and I connect vertex connected to the midpoint of the opposite side. All right, so you guys can see that in each case, no matter what the triangle looked like, if it was acute or obtuse or anything, that those three medians met at a point. Okay, the medians of a triangle, no matter what kind of triangle it is, will meet at that point. Meet at a point. The fact that the three medians of a triangle all intersect at the same point is known as concurrence. So it's similar to how all the angle bisectors and perpendicular bisectors were also concurrent. The medians, though, have a special relationship. All right, so we're going to look at that in exercise 2. So in the triangle below, midpoints D and E of sides A, B, and AC have been connected to vertices B and C to form medians C, D, and BE, which intersect at F. What are the two ways that DE and BC are related? All right, well, DE and BC, if this is a midpoint and this is a midpoint, then DE and BC, if you remember back from an earlier unit, they are parallel to each other. And that segment DE is called the midsegment, and DE is half of BC. Okay, we did this back in Unit 6. Now I want to make an argument for why triangle DEF, which is right here, DEF, okay, is similar to triangle CBF. So I got one highlighted in yellow and one highlighted in green, so you know which ones they're talking about. Well, remember, if these lines are parallel to each other, then that makes these angles right here congruent. Okay, I'll put some numbers in there just so I can say which angles I'm talking about. So angle 1 is congruent to angle 2. Angle 3 is congruent to angle 4. Because remember, the lines are parallel, so those are alternate interior angles. Therefore, the triangles are similar by angle. All right, now I want to prove that BF equals 2 times FE. So BF, which is this line right here, BF is 2 times FE, and CF is 2 times FD. Now remember, if the triangles are similar, the sides are in proportion. And I already know that DE and BC are in proportion, and that BC is twice DE. All right, so if it's 2 times as big, then every side has to be 2 times as big. So if triangles are similar, their sides are in proportion, and they will all have the same scale factor. Okay, they all are going to be that same ratio. So I already knew that 2 times DE equals BC, so that would mean that 2 times all the sides are equivalent to that corresponding side. So 2 times FE is equal to FB, and 2 times FD is equal to CF. All right, so this was true from the mid-segment theorem, and the rest are true because all the sides are in proportion, then they all have to have that same scale factor. Okay, so medians of a triangle. Here's the rule right here on that next page. The 3 medians of a triangle concurrently intersect. That means they all intersect at the same point, and it partitions or divides each other into a 2-to-1 ratio. All right, so they are in a 2-to-1 ratio. So in triangle DEF shown below, I have midpoints of sides DE and EF are marked as G and H. So that's right here. And segments FG and DH intersect at J. So this right here is that point of concurrency. If JH is 8 and FG, which is this whole segment right here, is 18, then I want to find the length of DJ. So let me just make a color here. So if this is 8 right here, all right, this segment is twice as big. Remember, it's a 2-to-1 ratio. So DJ equals 2 times JH. 2 times 8 is 16. And then I want to find the length of DH. Well, I just found out that this was 16, and 16 plus 8 is 24. And then I want to find the length of FJ. So basically, it's a 2-to-1 ratio, so I'm going to call that smaller section 1x, JG 1x, and I'm going to call FG 2x. And together, they equal 18. So 3x equals 18 and x equals 6. So FJ, which was 2x, or 2 times 6, is 12. All right, and you can tell by looking at them which one's the longer segment and which one's the smaller one. But the segment from the vertex to that point of concurrency called the centroid is twice as big as from the centroid to the side. All right. So we may be asked to construct a given median of a triangle, or even to construct the point where they intersect, which is called the centroid. So that point, like the point J right there, is the centroid. The point where those medians intersect, that point of concurrency has a name, and that name is called the centroid. All right? So we already know how to do 4, so we're going to skip 4. We've done midpoints tons of times. That's the one where we put our compass on A, we open it more than halfway, and we draw an arc, and then we go to B with the same setting, and we draw an arc, and where those 2 arcs meet, then that is that perpendicular bisector. Since it's a bisector, it would create the midpoint. Okay? And 5 is just more practice, but we've actually already done this. So the only thing that I really wanted you to learn from the lesson today is this right here. Those medians intersect at a point. That point is named the centroid, and that centroid divides the line into a 2-to-1 relationship. So there's a mathematical relationship that goes on, and we'll practice some of that tomorrow.